then you'll be fine. So this is all about sample preps. So in case of DNA, we extract DNA. In case of RNA, we make cDNA. And in the end, what we get is the DNA product. And in shotgun, you know that we break it into short fragments, right? And afterwards, we attach adapters. And then in NGS, our second generation, we amplify them. But in 3GS, third generation, we don't amplify them. We straight away go to sequencing reactions, and then this happens on the instruments like flow cells or the semiconductor chips, right? PTPs, picotitle plates. So these reactions, they happen over there, and then we get the images, and then images are processed into the raw read data, right? So here we are seeing the pairs of reads. So one is forward pair and one is the reverse. So basically it's a paired end data, and we can see that there are those red and green dots, the things we attached here, the adapters, they are also present here up till this stage, and you remove them in QC and filtration step, right? So FASTQ is the format in which this data appears, right? So what is a format? Format is way of presenting something or writing something. So you take the raw reads and they are still in FASTQ format, and you clean them where you remove those adapters, and then we go for some QC or QA steps. So up till this level, these reads are no more raw reads, but these are clean reads. Okay, what is a read, by the way? Read, a read fragment. So anybody, what is a read or a read fragment?
A sequence, sir.
Yeah, sequenced fragment, right? So you take the DNA as a big, uh, you know, lengthy molecule, and then you break it into small fragments. And when these fragments are processed and sequenced from within the sequencing machine or sequencer, the thing it returns, we call it as sequenced fragment or sequenced read fragment, or simply we call them as reads. For one, it's read, and for many, these are reads, right? So that's what we do. And then when we reach to this level, so what you do is now you have the clean reads, and in case you don't have the reference available, you will put them together on the basis of similarities, right, or overlaps. And then the finest thing which you get after so many steps, this thing is called as a reference, right? A reference. So use my essence fungi root beta. Right. So okay. So you take those clean reads, and then you put them together. And this process is called as assembly. We covered that. So which tool we used for? Let me go back. Which tool we used for quality assurance or QA? Right. So QA, and sometimes we call it QC. QC means quality control, and QA means quality assurance. So similar things. So which tool we used for quality assurance? Anybody? FASTQ.
Fast QC.
Very good. The data was in FASTQ format, and the tool name was FASTQC. Right. So it was basically FASTQ plus QC, and then they retained one of the Qs, right? And it looked nice. Rather, you can call it as FASTQ QC. So we said FASTQC, right? So that gives us some graphs or plots, and we check the quality of the data. If there is something wrong with that data, especially for an assembly project, or especially for a SNP calling, we want to have the data to be in really good quality, right? In differential expressions, we don't compromise on the quality, but we are not that strict or harsh, right? So here we need to have the strict parameters, especially in SNP calling, okay? So after the assembly, the thing which you get is called as the assembled genome or chromosome, or whichever level you are going. There are different levels we covered last week. So we put the reads together. The resultant thing is called as contig, right? And then you take the contigs and put them together, and then they are called as scaffolds. And then from scaffolds you go to chromosome level, and then in the end all chromosomes put together with orphan contigs or scaffolds, the additional assembled materials which are not fitting into either of those 24 human chromosomes or whatever species this. They are the extra pieces of the chromosomes or accessory regions. They are just put it there, right? So this reference you can get and download from the databases or web resources. One of the biggest one is obviously NCBI. So within that NCBI you can get them, but for humans, mostly we go with the UCSC, University of California, Santa Cruz. So it provides us the genome browsers, right? So where you can zoom in into different chromosomal regions, right? And then you can see, the nucleotide compositions, right? So when we align our sequences, we can also get the genome browsers, and we can see how many reads are aligning or mapping, and what are the similarities and what are the differences. Remember last week we had one tool, tablet. So that was a viewer. Browser is something which is even bigger than that. So that has the genome organized into chromosomes, and on that you have the tracks. So you have the tracks for the genomic regions, and you have the tracks for protein coding genes, and then next track is where you can see their RNAs or you can see their proteins, right? So that thing is called as a genome browser. So UCSC is very very established database or web resource. Obviously, databases are where you store the data, and for the accessibility of the community, you connect them with the help of some web page, right? So mostly web and database, they are always together. Okay, so you make a database. The people who are taking our database course, and then you can design its front end, and then in the end you connect both of them. Database part is called as back end, and where user interacts on the internet, this thing is called as front end. All right, so once the reference is formed, you try to find different genes within that. So once you assembled a larger script, then you need to read a script, right, coming from any languages. So you get different pages and chapters from some script written in ancient Roman or some other Greek or some other languages, right? You get them and then you put them together. So while you're putting that whole text thing together, that thing is called as assembly. And while you are reading that and while you are getting the messages out of it, that thing is called as annotation, right? Tarjuma, and then explanation, tashri. So in if you get the reference and you do annotation, the file which you get in the end is called as GFF, graphic file format. So far we are familiar with FASTQ, and now we will when we talk about annotations after those genome assemblies, we will also see this GFF format. If reference already exists, what we do is we take these clean reads that have been gone through QA steps, and we map them to the reference. This thing is called as mapping or alignment, right? And then here on this picture, you see there is that thick line. So that thick line represents your reference, when these individual arrows are your reads which are aligning to those references, right? And you just count them, or you can then compare them, like what you have here versus what you have here. In that case, you're doing snip calling. If you're just counting them and then you are trying to get the expression of different genes, suppose these are not the DNA but RNA reads, right? RNA fragments, you sequence them and then you let them go through some alignment tools or mappers, right? The tools are called as aligners or mappers, right? So mapping, they do mapping or alignment, right? So this is alignment or mapping, where you have the reference and this sequence is similar to what you have on the reference, and then they are aligning from here to here. For example, position number 20 to position number 120. This suppose read fragment is of size 100, so it's matching from here to here, right? So in that case, this thing is called as an alignment, right? And the format which you get after this alignment thing is done is called as BAM. BAM stands for binary alignment, and you also call alignment as mapping. So basically, this is an abbreviation, and for the sake of beauty, we retain both words. Otherwise, it could have been BM or it could have been BA, but BAM looks nicer. So BAM stands for binary alignment oblique mapping, or alignment slash mapping. Slash means this or this. Okay. Right, so then you get this raw BAM file after this alignment, and you remove the potential reads that can be the duplicates, and finally you get the reads which are, finally remaining. So in that case, this thing is called as a processed BAM, right? And then why these duplicates, they are here. Here we are not talking about the duplicates because of this speciation thing or this evolution thing where you get the homologs, right, or paralogs or orthologs, right? These are natural things. Homologs are the similar sequences. If they are there in different species, in that case you call them as orthologs, sorry. And if they are within the same species, like various repetitive regions in our genome, that's paralogs. Okay, so they are there, but this here we meant the PCR duplicate. So while we were having those original fragments, as we go back to the previous slide, so these three, they become 9. Everybody got 3 copies. So sometimes it happens that, like these, obviously these are the copies of the same fragment. The black one, these are from this blue one, and these were from this red one. And sometimes it happens like, normally all copies, they occupy the same cluster position within the sequencing reactions, right, or within that sequencing machine on the sequencing instruments. But if somehow they get duplicated, like this blue one of the copy moves from here to here, and then it's sequenced separately. um, Initially the sequencer throws the information to the system that these are 2 different reads, but actually they are the same ones. So they are the duplicates, they are the PCR duplicates. We don't like them here especially because while we are doing this snip calling thing, they are kind of giving us the double information, but that's not correct. So 2 reads starting and matching at the same point, starting at the same point and ending at the same point, but these are different. Like this guy starts from here and then this guy ends before this. If they are exactly the same, starting from the same position and ending at the same position, so they can be potentially the product of this PCR thing. So that's why this PCR thing in the second generation or next generation sequencing is disliked. So that's why in the third generation this PCR step has been removed. Okay. So here we covered about the base calls. Base calls mean which base is this, and then here we also talked about quality scores. So in FASTQ format, both the things are there. right? Initially, we were having FASTA format for the sequence thing and qual scores in another file. So FASTA file and a qual file, two different files we were getting as in 454, those initial sequencers, right? But later on, we realized like Illumina and other technologies, and obviously then 454 also followed. They they returned the file as a one big file with both FASTA sequence as well as these qual scores in one file, right? How these quality scores or quals are calculated, these numbers 30, 20, 70, 37, 26, what does that mean? So there are the tools that were you know invented for Human Genome Project by Ewing et al. One of them was Fred. So Fred was where what happens when a nucleotide is incorporated. Obviously, a colored wave comes out, right, with some specific wavelength, and then obviously it has frequency, and obviously you are detecting two things. Number one is the color of that peak, and obviously the height of that peak. So the peaks which are only one peaks where you have some background noise also, obviously all four uh, you know colors are all four nucleotides. They are provided to the sequencer. So some of the noise is there, background noise is there, but if that is too much noisy, obviously within that region, this quality score goes low, right? And then how these quality scores are calibrated? For that, we have the formula, and that formula is called as Fred quality score or Fred formula. So according to Fred formula, the P is the probability that a base is wrong. Suppose you have 10,000 copies of the same fragment, and all fragments are incorporating adenine nucleotide, then there is no error. But what if one of them is incorporating suppose cytosine or guanine? So what will happen over here is that one out of 10,000 is giving us the wrong signal. Obviously, it will not affect the quality very much, right? But what about 5,000 among us them are saying some different color or giving us some different nucleotide information, and half of them are giving another. So in that case, this 50-50 thing is quite confusing. So obviously that quality thing is really low. So that P over here is probability that a base is wrong. And then on this side, we take its negative, um, you know, we multiply this thing with minus 10 and we take its log to the base 10, right? So log to the base 10 of P is whereas, in log scale, you can deal with big numbers and you can bring them down, and you can deal with the really small numbers like fractions, and you can put them into a visible range, right? So that P is, for example, 1 out of 10,000, which is 0.0001, or 1 divided by 10,000, or 10 power minus 4. So if you plug in 10 power minus 4, the negative 10 multiplied by log to the base 10 of 10 power minus 4 is actually, the answer is minus 4 log to the base 10 of p. So p raised to power 10 power minus 4, the when you take its log to the base 10, it's minus 4. So minus 4 means 1 divided by 10 power plus 4. Okay. 10,000 in log to the base 10 is, so here we are representing the data in powers of 10, right? So for example, 1 means 10 power 1 in log to the base 10 scale. So that is 10, right? And 2 means 10 power 2, that is 100. 3 means 10 power 3, that is 1000. Similarly, on the other side, 1/10th or 100th or 1, thousandth, what do you call it, as the centimeter versus like decimeter, that is the 10 power minus 1, which is 1 divided by 10 power 1, so 1/10th. Okay. And then centi is 1 by 10 power minus 10 power 1 divided by 10 power 2, which is 1 by 100, right? So in normal calculations, this is 10 power minus 2, but when you take its negative, when you take its log to the base 10, so this thing is minus 2, right? And 1 by 1000 is minus 3, and 1 by 10,000 is minus 4. So you multiply minus 4 with minus 10, it becomes 40. So 40 is quite a good score, that only one nucleotide was wrongly incorporated into 10,000 copies of the same fragment. So that means 1 out of 10,000, that is the p here, 1 by 10,000, or 1 divided by 10 power 4, and when you bring it up it becomes 10 power minus 4, right? So p is equal to 10 minus raised to power minus q by 10. So if you have p, you can get q. If you have q, you can get p. So you plug in q here and you can get p. So q is also known as Fred quality scores, q scores, and they are also written as q Sanger, because initially we had this thing in Sanger sequencer. So that is the formula, and here are those calculations. What is the Q score for a base call with error rate of 10 power minus 6? When you plug in, it's 60. If Q is 40, what is P then? So P is 10 power minus Q by 10, which is 10 power minus 40 by 10, which is 10 power minus 4, which is 1 divided by 10,000, or 0.0001. So quality score 10 means 1 in 10 is the error. And what is the accuracy? Obviously, it's 1 minus error. So 1 minus 0.1, which is equal to 0.9. But what we do is probabilities, they always go from 0 to 1, and accuracies, they are showing here in terms of percentages. So probabilities and percentages, sometimes they are presented in parallel, right? But in terms of probability scale, this is 0.1, and obviously this is 0.9. In case of this accuracy scale, you can say 10% error and 90% accuracy, and 20 means 0.01 and 99%, and so on, right? Here we covered another formula called as Solexa score. So what happens here is we get the ratio between P and Q, right? So since P plus Q is equal to 1, if Q is equal to, some number X, obviously P is 1 minus X, right? Or you can also say that Q is 1 minus P, right? So P is 1 minus X if Q is X, or if Q has some, P has some value, so then Q is 1 minus that value of P. For example, 1 minus 10 power minus 4, right? 1 divided by 10 power 10 power 4, which is equal to 10,000. So 1 minus 0.0001. So that is 99.999. So that's the Solexa formula when you plug in. And then when another thing which they did over here was to fit in these scores into just one file, where you are having a nucleotide composition here as well as the score here in the same file. And initially we were going with these numbers. So what we got a problem here is that we had not this one-to-one correspondence of these symbols here, or these symbol on one side and number on other side. And secondly, these two digits, sometimes if you just our system deletes just one number, the whole sequence might change, right? And obviously this one versus two symbols, were taking the twice more resources, computing resources, obviously in terms of storage space and in terms of processing in the RAM or in the memory, right? So they came up with this idea, and for that what we realized were these symbols, they on computers, they have an associated value or a number which is called as ASCII value. So that's why these characters are called as ASCII characters, right? So these numbers are then translated into binaries or binary codes. So ASCII value for space character is 32, and that is then translated into this binary code like this. Okay, this is a funny picture, and these are their binaries. So T is here, H is here, I is here, and so on, right? So if you click in here, you can get an ASCII converter where you can see when you press any key on the keypad, so there is an ASCII number or value that is invoked, and then at the computer's level, at the hardware level, those binaries, obviously it's all about electricity, electrons going in and out to the system, so that they are translated into those binary codes, where zero means the electric current, presence of electric current, and zero means no current, and one means yes. Okay, so there is a current that flows through the system, right? So anyways, so here are those visible characters which actually start from 33. So when a score of 0 was placed here, we realized that 0 was not there in that list of those visible characters. So anything beneath 33 are special characters. So like 32 is space, and then you have tab characters, and then you have new line character, carriage return when you press enter, right? Or when you press delete button, obviously it has a different ASCII value which is not in that visible range. So these are not actual physical characters, special characters we call them. So the actual characters like sign of exclamation starts with the ASCII value of 33. So they are present 33 onwards. So in the raw score, if it is 0, we add 33 to it and we put sign of exclamation, right? In Solexa, we use this formula, but they since they had those numbers here, which are because of that formula and because of that ratio thing, the minimum possible value was -5 and maximum was 40. Here minimum was 0 to 40, right? So all positive numbers. Here there was some negative number. So if we start with something like 33, so -5 minus 33, the actual number, if you take -5 and you add 33 in it, see the actual number becomes 27. So that 27 is again not that visible. So what they did was they added this number 64, and when you add -5, when you add 64 to -5, it becomes 59. So they started from here, this sign of this semicolon onwards. What Illumina did was a wonderful thing. So they came up with the Fred formula, this formula from here, Sanger, and offset from this Solexa, and obviously it's a new thing. So nobody can challenge you. So they start with this 64. So within 0 they added 64 and they started with add sign. A was 65, B was 66. So if you see a B character, B means bad, or A means also bad, and add sign means 0, right? So that quality score is 66 minus what you have added here. This thing is called as offset. So here the offset is 33. So if you see this sign of exclamation, your actual score is not 33. You need to take that 33 thing back from this. So the actual score is then 33 minus 33, since you added that, so the actual score was 0, right? So if you see 59 in Solexa, that's -5, 64 in Illumina, that is your 0, right? But 64 in Sanger is quite a good score, right? So that's where that scoring scheme is important. We need to remember that, or we need to, just the sequencing companies actually tell us that which scoring scheme we have used. Sometimes the tools, software, they are smart enough to recognize those scoring schemes themselves. They know that in Fred quality scores, maximum you can go from here to here. So if you are seeing any characters which are beyond the range or scope of Sanger, so that is something which is coming from here or something that is coming from here. So sometimes they judge from those symbols themselves, but sometimes you need to provide it to the tools. Okay. In QC, we talked about box plots. I'm sorry. So here what we do is you take those nucleotide compositions, you take those reads, and then you take, and in parallel you also take their quality scores, and then those quality scores are translated into the actual scores. Obviously their ASCII number or value minus this the offset thing, okay, and that's your actual score. By the way, these may not be corresponding exactly to this. This is just an example which we created just to let you know that this thing is happening. So either you are taking those bases and you're calculating like how many position number one of all reads, you take all those reads, you stack them together, right, like a plates, in a container or in your what do you call, drawer, right, where you put your utensils. So we have those nucleotides on position number one. So their composition is GAC, so 33% each, so three of them. And at position number two, all T, so 100% T, A 0%, G 0%, or you can also go with the probability scale, right? So 0.25 in case you have all four, you have four reads and you have all four, so in that case their proportion, so ideally they should be like 25% each, but obviously we know that GC content varies. So obviously when GC is higher, obviously AT is a little bit lower than that. So we also check for that. We also take those quality scores, and we, since these are numbers, so we can take the summary statistics, so we can get the mean, mod, median, or we can get those box plots and we can see how the trend goes. So these are the box plots of quality scores. These boxes indicate the middle class. So up till this point, this where this box starts, so these are your lower 25% of the population, right? So you have these numbers, so you get their average or you get the midpoint, right, the middle point. So you calculate, you sort them and you get their midpoint, the medians, which are here. So that is where 50% of the population is up till that red line within that box. So some of the boxes are very, very symmetric, like this one. Ideally they should be like that, but most of them are very, very highly non-symmetric. That's why this data is not a normal data. It's not normally distributed. In normally distributed, this box plot is quite symmetric. You can see a bell-shaped pattern. If you draw that distribution, we covered that, right? So here you have the lower 25% of the population, and here is obviously your means, and you're connecting the means on through this line. All boxes in green zone means that it is of good quality, minimum as 28, or let's suppose 26. Some are there in the in the acceptable region, the yellow one. Red one is where you should be cautious, right? So here some of them are ranging from as low as 14 or 12 and as high as 32. So we probably gonna use trimmers or clippers for them, different tools which are there in that FastQC thing. Right, so we had this FastQC in Linux, and then we also talked about the assembly. In assembly, maybe I think we should practice some hands-on. So let's go again. Those people who are having difficulties, just let me know. I was just wondering whether we get some messages here due to raining. There is a network issue. Thanks God there is raining. Where is raining? Rubaiya Farid. Where is rain?
Sir, in Kashmir.
So we are waiting since midnight, and everyone, Archane, thanks God, it started from Kashmir, and we believe tonight or tomorrow it will be in Islamabad, and day after it will be in Lahore, right? And somewhere in December it will be in Karachi also, right? But we definitely need that. Which part of Kashmir? Rawalakot? कहाँ पे हो आप? It must be colder up there. बाग सर्दी शुरू होगी?
अच्छी खासी शुरू हुई है यहाँ तो हम लोग तो काफी टाइम से स्वेटर्स यूज कर रहे हैं यहाँ पर.
Very good, lucky people. Right, so we are just waiting. So anyway, so what we do over here is, you get those reads, you put them together. This thing is called as de novo. De novo means if you're doing it for the first time or you're doing it from scratch. Once if you do assembly and this thing becomes a reference, so if you have the reference available, like human genome, the first one which they did in year 2000 was the I'm sorry, de novo thing. And when once they, when people started sequencing their own representative genomes from different populations, so that thing is called as resequencing. So we were just comparing with the reference. So here there is this assembly thing, and here there is this alignment thing or mapping thing. So in that case, you can call it as a resequencing project. Obviously, resequencing means resequencing. You're doing it second time or third time, right? So you originally sequenced that, but then you resequenced. This example I gave to talk about the complexity of the problem. So the stanza comes from A Tale of Two Cities. The videos there on the YouTube. So if you just click, you can just see them, right? And here is there is the scene in the movie where you can see the rich people are enjoying the parties and on their side, and then this dialogue is somebody speaking, it was the best of time, and then he shows the poor who are fighting on bread, and they were not doing good, and there was a big difference between the poor and the rich. And on one side it was the age of wisdom, and on one side it was the age of foolishness. A tale of two cities. So one city is obviously Paris, France, and then this gentleman runs to that lady. Actually, her father, she thinks she lost him, but he was imprisoned somewhere, or then one person comes in and tells her that your father is alive and he's there, and then I think she travels to London, and this gentleman also travels to London, right? And then he's mistakenly taken as in custody in place of another culprit. And so overall, it's basically that French Revolution thing was here, that was picturized as you see in that picture. I mean, that's about the movie and that's about the book. So where you can see they are hanging some rich people, or they are beheading somebody, right? So that difference got so much that people started, if anybody um, belonging to the upper class or rich class or the ruling class, they started beheading them. So that was a very terrible thing that happened in the history. This problem or this stanza, if you see in DNA shape, it looks like this, because in DNA you don't have commas and full stops and space characters and new line characters, though we have them in the shape of introns, exons, or coding or non-coding regions, but they are all like ATGCs. Okay, you just need to find a pattern that is the non-coding in between. So that's where we say that exon starts, and that's where we say the ORF starts, where you get the first triplet as ATG and ending it at UAA or UAG or UGA, right? So that is where your stop codons are, right? So that thing is called as an ORF, and then you know that there is a promoter sequence and blah blah blah, so many other patterns or sequences. But that's the complexity of the problem. So when you do those short sequence reads, they become like this, and your job is to put them together. So the moral of the story is that assembly is not that easy task. And these are the steps that happen in the assembly. We covered that when you put the sequences together, the reads together on the basis of overlaps, thing is called contig. Contigs put together, the thing is called scaffold, right? And sometimes those scaffold are spaced with some region that is we have not sequenced yet, or obviously for that we don't have any evidence present. So we put some ends, and means any nucleotides or gaps here. So contigs are put together into scaffolds with what we call them as captured or padded gaps, right? So reads put together into contigs and contigs put together into scaffold. And this is the algorithm. We talked about like a tribute to Al-Khwarizmi. His book was Kitab al-Hisab al-Hindi. and that was translated into, I guess, Greek, this Latin language. So algorithmi de numero indurum Al-Khwarizmi on the Indian numerals, that's what we translated into English. So this Al-Khwarizm, the word Al-Khwarizm, and then the word came like algorithm, right? So different algorithms. Here are Alpaths and Velvet and Miraculous. Here we also covered the coverage. So coverage is n times L divided by G. Total number of reads is n. Length of a read is L, and genome size is G. Overall, we represent this thing as X, right? So there is one example. So Illumina produced 1 million reads of 100 base pair in length for species. So 1 million is number of reads multiplied by length of one read. So into 100, that makes 100 million, divided by a species whose genome is 1 MB, 1 million bases, right? So divided by 1 million, so 1 million cancels, and you get coverage as 100x, which is excellent, or which is awesome. Okay, so any assembly project is okay if your coverage is beyond 30x. 50 is a good number and 100 is an excellent number. Normally what we have seen is the people, they barely make a coverage of more than 30x, right? Because obviously it's expensive. So that means initially in the startup material, you should have at least 30 copies of your genome. So obviously for larger genomes, we are not doing PCR thing, but what we do is we start with the instructions from sequencing company. They tell us like if your DNA, purified DNA is that microgram or whatever nanogram, so it will have, you know, expectedly that many copies of your target genome, right? But this coverage is uneven. In reality, some of the regions, they get good fragments and they get sequenced very well. So some of the regions might be missing, but overall the average coverage, once we assemble them, that coverage is again recalculated. So again we recheck. So at the average all across the positions, it should be more than 30x. So in that case, it's a good number. Another problem that happens in the assemblies was the repeats. So sometimes it happens that this region R1 and R2 is merged together as one copy, right? And this portion comes out as an orphan contage. I'm waiting for our own Azan, and then I can take a break, and then after that we can do the hands-on. So the paired end sequencing technology actually helps resolving those repeats. Then we talked about the assembly algorithms. So one of them was de Bruyn's. So in de Bruyn's, we talked about K-mers. So in K-mers, you take the original reads and you break it into further small pieces. Like here, K-mer size or K is equal to 3, right? So in this way, you can take that thing and you can have its that many pieces. I guess 8 or 9 of them, 8 of them probably. How many? 1, 2, 3, 4, 5, 6, 7, and 8. Obviously, you cannot go beyond this, so you just leave the last two characters. So total here there were 10 of them, so we can make 8 k-mers of size equal to 3, right? And same for the next read fragment and the next and this one. And with the help of that, those tools like Velvet, they solve this assembly problem real quick, right? Let me take a pause.